للعالمين.
Some others as well. So let's rewind back to week 2, where we introduced you to your very first data structure. That is an array. And an array, recall, was just a chunk of memory whereby elements were stored by design back to back to back. It's an array of contiguous memory specifically. So with an array, we could certainly store not just one thing, but 2 or 3 or even more. And so, for instance, if we treat my computer's memory as this sort of abstraction here, and pictured here are 3 bytes or some multiplication thereof, suppose we're storing in the computer's memory an array of size 3, storing the digits 1, 2, and 3. Well, remember that if we zoom out per last week, there's other stuff going on in memory. So even if we want to add another number to this array that we didn't think of when we first started the program, like the number 4, ideally we would put it right here next to it. Otherwise, it's no longer an array. So by definition, if we're using an array, it's got to end up right there after the 3. But what else is going on inside of your computer's memory? Well, assuming your program is of any length and you've got other variables, other functions, you've been running it for a while, there's a lot going on and your memory is being used and reused. So for instance, somewhere in memory might be immediately adjacent to this, like hello, comma, world, \0, the null character, just because maybe you have another variable somewhere in there that is storing that particular string alongside your existing array of size 3. And all of these Oscar the Grouches here really just represent what we called last week garbage values. Like there's obviously bits there because they don't disappear. They're always going to be inside of the computer somehow implemented, but we don't really know or care what they are. They're the remnants of those bytes having been used for other older variables, previous function calls, or the like. But the problem clearly here is that, OK, 1, 2, 3 is there, but the h is here. And unless I want to start taking a byte out of my string by overriding the h with a 4, like we just can't fit it right there. And yet, even though there's Oscars all over the place, those are indeed garbage values. And therefore, we could use that space because it's technically unused. We just don't know or care what the values are. So where could I put 1, 2, 3, 4? Well, my gosh, like I have all this memory down here that's unused. I could certainly change those garbage values to be 1, 2, 3, 4. But to do that, I might need to do a bit of work here, right? It's not just a matter of just saying boom and it happens. Now with C and with code, I'd have to do this a little more methodically. So let me abstract away everything else that's a distraction. Let me assume that there is indeed at least 4 bytes available for 4 numbers just down here, though we could have put them in a bunch of different spots. What's involved now in moving the 1, 2, 3 to this new chunk of memory so we can add the 4? Well, I think conceptually we're going to have to copy the 1 from old to new, copy the 2 from old to new, copy the 3 from old to new, and then ultimately we can get rid of the old memory. Those 3 original bytes could now look like Oscar the Grouch and just be garbage values for all intents and purposes. But now I have room for a 4th byte wherein I can put the number 4. So this is nice, but what's a downside of this approach? What's a downside of solving the problem in this way, where the problem at hand is just to grow the array, so to speak, to increase its size, to fit 1 or more numbers? Seems pretty straightforward, but yeah. OK, maybe it's out of order, but I think that's OK because the order just matters that it's relative. So long it's still contiguous, back to back to back in a different chunk of memory, I think we're OK there. It's not like I changed it to 4, 3, 2, 1, but a reasonable hunch, yeah. Yeah, like I didn't really plan ahead here. Like if I have to add another number like 5 or anything else, well, I might have to jump through these hoops again. Maybe I get lucky and maybe there's space there, but not if I have other variables and other things going on. That too might be used at some point. Other thoughts? Yeah. Slow efficiency, why? Yeah, I mean, it's just inefficient. It's sort of bad design, arguably. Why? Because I had to copy all of my original work down here. And as you note, if I want to add a 5th number, I'm going to have to copy it again and again and again and do things n times again and again. Now, maybe that's necessary. We'll soon see for sure. But it feels like this is not going to end well, especially if the array isn't of size 3 or 4, but 300, 400. Your computer ends up spending so much time just spinning its wheels. I mean, honestly, better might be this. Like if this is my same array, physically incarnated now, 1, 2, 3. It's literally on the edge of the shelf, so there's no room for the number 4. You know, maybe where we could take this story is, well, let's just find room for the 4. Like let's just put the 4, for instance, over here, replacing some available garbage value, some spare byte over here. But now, wait a minute. I've broken the definition of an array, right? I can't have 1, 2, 3, and then 4 over here. So maybe there could be a mechanism if I put this thing on again, where when you get to the end of the existing elements, maybe I just somehow digitally point to the 4th array. And maybe we can kind of stitch together all of these different values in memory so that if you follow the arrows, so to speak, we can reconstruct exactly what the order is, even without having to find or make room here or pick up all of these numbers and move all of them over there. So that's perhaps the direction in which we'll go here. So let's see how we might get to that spot as follows. Let me go ahead and open up, say, VS Code here. Let me open up a program called list.c in my terminal. And let me go ahead and whip up a relatively simple program that just demonstrates what we did back in week 2 when we introduced arrays as follows. Let me include standard io.h so we can print stuff out. Let me do int main void, no command line arguments for now. Let me give myself an array called list of size 3, and I'll just hard code it to keep it simple for lecture's sake, each of which is going to be an integer. And now just so we have some specifics to talk about, let me put it list bracket 0, the number 1, list bracket 1, the number 2, and list bracket 2, the number 3. So I'm just translating into code what we just had pictorially on the screen and also physically here with these numbers on the desk. Now let's just do something mildly useful for this. How about we do for int I gets 0, I is less than 3, I plus plus. Let's just print each of these numbers out just to make sure they're indeed in memory as I intended. So %i \n, comma I, and then a semicolon. And I think that's it for now. So nothing interesting, no problem solved just yet, just a proof of concept so that now when I clear my terminal and run make list, no apparent errors at the terminal. And so when I now do /list, I should see, hopefully from left to right, 1, 2, 3. But of course, if I want to add a 4th number now, there's no mechanism for such, certainly in the code that I just wrote. I could go back in here and change this to a 4. I could go down here and change list bracket 3 equals 4. I could just manually change the code, recompile the code. But of course, that doesn't give me any additional runway for the 5th or 6th number. So let me try to take a different approach, drawing some inspiration from last week. If I want to allocate memory dynamically, maybe because I don't know when I wrote the program how many bytes I want, we have another function as of last week that does not require that you commit in advance to a certain number of bytes. Via what function can you just ask the operating system for a chunk of memory? OK, so malloc, to allocate memory. Now, an array is just a chunk of memory. And even though since week 2, we've been using this syntactic sugar, this convenience of just using square brackets and indexing into it, it's just making it easier to manipulate a chunk of memory that's contiguous, all together, back to back to back. So today, just like last week, we can take those sort of training wheels off and maybe be a little more deliberate in how we allocate memory. Let me go, for instance, and do this. Let me delete my contents of my main function here, go back into main, and let me propose now that I declare, for instance, how about my list no longer as an array, but as a pointer. So int star list, and I'm going to go ahead and initialize this to be, how about a chunk of 3 integers for now? So I'm still going to hard code it, but I'm taking a step toward more dynamism for now. So let me allocate 3 times whatever the size is of an int, but it's usually going to be 4 bytes as we know. So this is really going to be 3 times 4 equals 12, but it's a little more dynamic. And now what can I do down here? Well, this is just a chunk of memory. So I can do literally list bracket 0 equals 1, list bracket 1 equals 2, list bracket 2 equals 3. And voila, achieve the exact same effect. Because again, an array is just a chunk of contiguous memory. But malloc gives you any old chunk of contiguous memory, so you can rather treat one like the other here. Now, if you really want to be cool, you could do something like this instead. You could dereference the address in list and go there. You could go down here and dereference list plus 1 and go there. But honestly, no one really writes code like this. It's just too cryptic. It's a little too far over the line, at least for most people. And so I think the syntactic sugar, as I keep describing it, just the more user-friendly square bracket notation, does the exact same thing, figures out the pointer arithmetic, and puts each of these integers in the right chunks therein. Now, just to be super pedantic, let me make sure if something went wrong. So if list equals null, that means that something went wrong, like my computer is out of memory, which we should check for typically. So let me just immediately return 1, signaling anything other than 0, which means success typically, just to get out of this program because something's wrong. But now let me propose that I've had a, well, let's do this. For int I gets 0, I less than 3, I plus plus. Though a better design would always be to use a const, but I'm just doing this for demonstration's sake. Let's print out each of these ints too, and just make sure I didn't mess anything up. And let me open my terminal window again. Let me do make list again. OK, implicitly declaring library function malloc with type void star something something. Implicitly declaring is the operative words there. What did I mess up? Yeah. Yeah, I forgot the header file in which malloc is declared. I remember now, OK, that's in standard lib.h. And it's fine to look stuff like that up if you forget. So let me include standard lib.h. Now let me clear my terminal, run make list again. OK, now we're good. /list. And now what did I do wrong? Oh, OK. Not intended, but teachable moment. What did I do wrong? Yeah. Yeah, I'm printing the values of I instead of what is at location I in the array. So what I actually meant to do was print this out, thank you. So now let me recompile, make list, /list. And now, OK, those are the 3 values I was expecting, not the indices thereof. Now let me propose that for the sake of discussion that I regret having only allocated space for 3 integers. And maybe I really should have allocated enough space for 4. Now, this is not how you would do this in practice, because presumably if you have a change of thought, just go back in and correct the code. But let me propose that somewhere in here is a more complicated program and time passes, ... There's a lot of other interesting code there. But at some point, I might want to give myself more memory. So how can I do this? Well, let me just ask the operating system now for 4 new bytes of memory so that we can, at least in version 1, implement the idea on the board where I just copied the 3 bytes into the new 4 bytes and then added a 4th value. So I'm going to use malloc again, and I'm going to say here's a new pointer. I'll call it temp. TMP for short, which is quite common when you just need it briefly. I'm going to then call malloc again. I'm going to say give me 4 integers using size of. Let me again make sure. So if temp equals null, something went wrong. So let me just immediately return 1. And for good measure, before I return 1, let me free the original list so that I don't leak memory. So I'm not just immediately returning 1. I'm being a good citizen and remembering, well, if this malloc call did succeed, and indeed I got as far as line 18, but then line 18 failed, I should free the memory that I previously mallocked. So again, that's the rule of thumb. If you allocate it, you should be the one to free it, even before you're about to quit. Now, once I've done that, I think I need to do what we did pictorially on the screen, where I need to copy the 1, the 2, the 3 from the old array into the new. So how might I do this? Well, let me give myself a loop. So for int I gets 0, I less than 3, I plus plus, because the size of the original is still the same. Let me go ahead and treat the new chunk of memory called temp as an array itself. And so I can absolutely use these square brackets just like before. It's just a chunk of memory. I'm treating it like an array. And let me add to that value whatever's at the original list at location I as well. So this, again, is just this exercise of copying from old to new, step by step, the 1, the 2, and the 3. But I still need one additional step. If my goal at hand now is to have ultimately a 4th value here, well, I'm just going to hard code this for demonstration's sake. And I'm going to go to the very last location of temp, which is of size 4, which means the last element in temp is temp bracket 3, because it's 0 indexed, but there's 4 total spaces there. And I'm just going to arbitrarily, for the sake of discussion, put the number 4 there. And that is what happened when we proposed changing the final garbage value there to that 4. But now I need to do what the slide did for us sort of magically on the screen. I should now do a couple of final things. I should free the original list, which I've not done yet, because I only called free earlier in cases of error, and that was just to be safe. I can now free the list. And now if I want to inform the computer that I want list, quote unquote, my variable called list, to point at not the old chunk like it originally did, but the new chunk, I think I can just do this. List equals TMP. And again, that's just saying that if list is a pointer, which it was, because look at the very top line here. On line 6, I declared list to be a pointer to a chunk of memory. Temp, meanwhile, is a separate pointer to a chunk of memory. So down here, this line 33 is just a matter of my saying, OK, now, henceforth, because I've already freed the old chunk of memory, my list variable should point not at this chunk of 3 bytes, but this chunk of 4 bytes, or really 12 in total now. Or rather, 16 now, because we have 4 such bytes. Questions now on this code, the point of which was quite simply to demonstrate how we could implement in code this idea of fairly correctly but inefficiently allocating a new array of sufficient size and then populating it with a new 4th value. Questions on what we've just done here? No? Yeah. Good question. At this point in the story, with line 33, do I not have 2 different variables pointing at the same chunk of memory? Short answer, yes. But here's where the semantics are perhaps compelling. List is the variable that I intend to use longer term and keep around in memory. And again, assume that there's even more code going on here that we just didn't write yet. So it's useful to have that variable. Temp was just kind of a necessary evil, because up here, it would not have been correct to do this. It would not have been correct to say list on line 18 equals the new chunk of memory, because this would have represented a memory leak. If I prematurely change temp to point not at the old chunk but the new chunk, at that point, no one's pointing at the old chunk, and so I've lost those 3 bytes. Valgrind, for instance, would yell at you for having lost as many bytes in memory. So in this case here, I do leave this as temp. Yes, it's duplicative at this point, but it's not a huge deal if it was just meant semantically to be a temporary value. But down here, at the risk of one more line of code, I still want to be a good citizen, free list, and maybe just for good measure, return 0 explicitly. But notice, it's not doing it twice per se. On line 31, what am I freeing? The original address of list, the 3 integer version. Then I change what list points at. So it's pointing at a completely different chunk of memory, this one of size 4. So eventually, when I'm all done using this memory for this demonstration, I still need to free list. But at this point in the story, line 40, it's pointing at the new chunk of memory, which I similarly need to hand back to the operating system by free. Yeah? When would temp equal null? So let me scroll back up slightly. This is being a good citizen and a good programmer. Whenever it comes to using malloc, malloc can return null if the computer is out of memory. So this is maybe a much bigger program. You've got other things going on in it. And so you just don't have enough memory available to be handed. Malloc needs to signal to you that there's some error. And so it will, by convention, per the documentation, per the manual pages, return null. So this is just me being a good citizen. Otherwise, here's another error that might cause your program to crash with a segmentation fault. If you get back null, but you assume that it's good memory, going to address 0, aka null, will crash your program intentionally. Yeah? Correct. If I were to change my final line 40 here to be free temp, this would also work as well. And here, this is really a matter of design. It's a very nitpicky thing. We could probably debate it. But because at this point in the story, my main variable for remembering where the list is called list, this is sort of the more responsible way to do it, freeing the list, just so that my colleagues, my TA, doesn't sort of wonder, why are you freeing temporary memory that you already freed? Like, it just is a semantic thing at this point. But good instinct. It would also work, correct? Maybe just not good design. All right, so it turns out that this gets annoying quickly, as it did in the picture of doing all of this duplication. And even though technically it's necessary to copy those values if you need a newer, bigger chunk of memory, there is at least a function in C that simplifies a lot of this for us. And in fact, let me go ahead and do this. Instead of using malloc this second time on line 18, in addition to the first time I used it on line 6, I'm actually going to try and introduce another function called realloc. which, as the name suggests, tries to reallocate memory for you. And it works a little differently from malloc. Realloc expects two arguments. The first one is, what is the chunk of memory that you want to try to grow or shrink? That is, reallocate to be a different size. And then you specify what size you would want. And indeed, in this case, I want 4 times size of int. And that will now give me, hopefully, a new address of a chunk of memory that's big enough to fit all 4 numbers. But what's wonderful about realloc is that it will handle all of the copying for me. So in fact, I'm going to go down here. I'm going to get rid of all of this extra for loop. And what I'm simply going to do instead is this. Once I can trust, after lines 18 through 23, that realloc worked and it didn't return null because I'm out of memory, I can just say, OK, just immediately remember that the new list points at this new chunk of memory instead. And then I can still now do this line, but I can tweak the semantics here and just say list bracket 3, the new final location in the new list is 4. I don't need to free this here. I don't need to do this. All I need now at the bottom is the final for loop to just print out these values. So in short, even though that was somewhat quick, using realloc just moves the entire copying process that I implemented myself a moment ago using a for loop. It just moves it to realloc and lets it deal with the copying for me. It's no more efficient, but at least means I'm writing less code, which is more pleasant. And hopefully the people who wrote malloc or realloc are smarter than me, and they just will introduce bugs with lower probability too. All right, that was a lot. Any questions? Good question. Why do you still need to make list equal temp as I did on line 24? So ideally, I would do this. Ideally, I would just change this line 18 to be list. That is to say, or actually, even better, ideally, I would just say realloc this list to be of this new size. But again, things can go wrong when allocating memory. You need to check a return value to see if it was successful or not. And so we need to use a return value. OK, so let's not introduce temp. Let's just use list. But here's where a memory leak might happen. In the off chance realloc fails and doesn't have enough memory for your 4 bytes. Therefore, it returns by definition null. You can't overwrite the original value of list with null to then check it. Why? Because now who remembers where the original 3 bytes were? If you prematurely change the value of list, you've lost. You've leaked memory in that sense. And so that's why, let me undo this change, I declare a temporary pointer for the sole purpose of making sure I can check the return value. And then once it's good, now I'll update the value of list. So it's sort of doing a switcheroo by making sure first that you have a new value to swap with the old. Other questions on this code? Yeah? Indeed, realloc automatically frees the previous memory for you. And better yet, it's even smarter than that. If you get lucky and there happens to be space right after your existing chunk of memory, so 1, 2, 3 garbage value, instead of 1, 2, 3 hello world, realloc won't even bother copying things from old to new. It will just say, OK, I'm going to now reserve for you more bytes than you originally asked for, so it doesn't have to waste time doing that copying. And so in that sense, this version is now not only still correct, it's even better designed because we're not wasting time with that for loop. We might have to resort to it if there is, in fact, hello world or something else in the way, but hopefully we'll get lucky and save those steps. Other questions on this manipulation of code here? Yeah, in the middle. What if you want to resize a 2-dimensional array? So very similar in spirit, whereby you can use the same trickery. Let me wave my hand at that for now, just because I think that's going to sort of significantly increase the complexity, but very same primitives. Ultimately, a 2-dimensional array is essentially just a doubly long or quadratically longer list of memory that, using square bracket notation, is doing some of that mental math for you. But it's fundamentally no different of what's going on underneath the hood.